Let's begin looking into exception handling in ARM Cortex M4. Now, as you know, interrupts are a common feature available in almost all microcontrollers. So, if you have experience with microcontrollers previously, say for 8-bit, 16-bit, or any microcontrollers for that matter, exceptions have to be a part of the microcontroller architecture. Now, in this case, we will use the term exceptions and interrupts interchangeably. And then we will, later on, we'll see that they are slightly different in, in the case of ARM Cortex parlance. Yeah. So, interrupts are typically generated by hardware like peripherals or external input pins. That is, peripherals could mean your universal asynchronous receiver transmitter or UART peripheral. It could mean your USB. It could mean your timers. It could mean anything which is considered as a peripheral. And all peripherals can generate interrupts due to certain events. Now, whenever an interrupt is generated, it causes a deviation in the actual flow control of the program. In the sense, say you have written a main program and your code is executing in a particular path, and suppose you are doing some calculations in the main loop and some interrupt comes in. At that point, wherever you are at that point in the code has to be saved. The interrupt service routine has to be executed. So even now, between the main and the interrupt service routine, of course, there will be some interrupt latency, which we'll be talking about later. The interrupt service routine gets executed, and all the registers are restored to their previous values, that is, before leaving main, and the execution in main continues as if nothing ever happened. In the sense, the main doesn't even realize that an interrupt had occurred. Now, the main controller in the case of, or the main unit of interrupt control in the case of Cortex M4 is the nested vector interrupt controller, which we will be calling, the acronym for it is NVIC, so we'll be calling it as NVIC henceforth. Now, there are four major steps that happens when an interrupt is asserted. Now, this is something that we just spoke about, and it's very generic, and that is the peripheral asserts an interrupt request to the processor. Now, the processor suspends the currently executing task. So when we say task, say this could be the main program flow control. Say it's some function that you're executing in your embedded code, and then that code is suspended. That is, if the program counter was counting and moving from instruction to instruction and executing that particular series of instructions, it is going to stop there. It is not going to proceed any further. What it will do instead is it will execute the interrupt service routine to service the peripheral. And once when the peripheral gets started to service, it is going to clear the interrupt request. We'll see all of this as we go along through the course. Then the processor resumes the previously suspended task. So a lot more things happen between these steps, okay, and we are going to see them one by one. Now, in Cortex-M processors, some of the registers are saved on the stack when an exception occurs. Okay. Now, this is a very important feature of this particular architecture, that some registers are saved onto the stack automatically and they are restored automatically as well. Now, this essentially means that it sheds the burden of the programmer to save these registers on their own. Say if you are doing assembly programming, in that case, you would need to save these registers on your own before moving on to the interrupt subroutine. In this case, in the case of Cortex-M, that is not the case. The saving of a few registers which fall in the AAPCS are done automatically. So you are spared of that burden. Okay, and exceptions, again, the exception numbering in Cortex-M4 is a bit strange. We'll see that because you can see the exceptions in different lights. For example, exceptions start, it is numbered from 1 to 15, and then the peripheral exception number starts from 16. But then again, when you name the exceptions as interrupts, that is 1 to 15 could be called as exceptions, and then 16 is an exception. But when you start calling that 16th interrupt as an interrupt, the number becomes 0. That is, the numbering convention becomes 0. Now, this is a rough block diagram. So as we discussed about the NVIC, you can see it here. The green block is the NVIC. You have the peripherals, you have the processor core, and of course, I mean the I/O pins also as a part of the peripherals here. So you could have an extra block here, which are the I/O pins, and you have a SysTick block in here. Now, the reason why the SysTick block is mentioned here, which is also an interrupt, is because as you know, since the Cortex-M4 core, okay, has a common architecture across different vendor SoCs. Okay, so the Cortex-M4 core has to be the same, and the vendor is free to add the peripherals as it wishes. Okay, so the SysTick is a generic interrupt which is available in all Cortex-M4 cores. These peripherals might be varying, but the SysTick is common. So portability becomes easy. So any code you write on one microcontroller family, if you have actually ported a real-time kernel to one of these microcontrollers which utilizes a SysTick, that particular kernel would be more easily ported to another Cortex-M4 controller, because the SysTick is a generic timer which is inherent to the ARM Cortex architecture. Okay, so we have to distinguish between the ARM Cortex core architecture and the additions that the particular vendor will do based on the peripherals. Okay, all of them follow the ARM architecture paradigm, but then there is a lot of freedom in what you do with your peripherals. So depending on the usage, depending on the capability of the processor, this part is going to vary. Now, there are some system interrupts also coming from the processor core to the NVIC, which is not shown here, but there will be some system interrupts also which is going to come into the NVIC. So the NVIC will actually have a non-maskable interrupt. We'll talk about that later. It will have interrupt requests. It will have some system interrupts like hard fault and so on. And of course the SysTick. So all of them come into the NVIC, and the NVIC is actually responsible for handling, scheduling the interrupts. Now, these are the different modes that the ARM processor can be in. Okay, so there are 3 modes basically. So when your program is just executing, say in your main or in some function without an interrupt, it can be in 2 modes. That is, it can be in privileged mode and an unprivileged mode, and this mode is called a thread mode. Now, thread mode is basically the normal mode that the program runs in. Handler mode is when an interrupt occurs. So when an interrupt occurs, it can occur from the thread mode, and it can occur from the thread mode unprivileged. So thread mode privileged and thread mode unprivileged. But as you can see, thread mode unprivileged cannot go into the thread mode privileged. Privileged can do a lot of things. From privileged, you can move to unprivileged, but it is not the other way around. Okay, so any thread in the unprivileged mode, if it needs to access certain peripherals which it cannot otherwise, it will raise certain software interrupts, going to the handler mode, do its job, and come back. This is typically seen when for RTOS tasks, basically. So some tasks will not have the privilege of actually accessing the peripherals or certain regions of the memory directly. So it has to first go into the handler mode, do its job, and come back. So this is for security reasons, as there has to be a division between which applications can access sensitive areas of code and peripherals.